Okay, so this is going to be a video on my last assignment, CA3. But before that, let's talk about some historical backgrounds, basic properties, etc., etc. So it originates from early origins come from Babylonians from 4th century BCE, and then later on you move on to ancient Chinese, where they use similar methods to Gaussian elimination to solve simultaneous equations. And then much later on in 1800s, you get the name from James Joseph Sylvester, some formal definitions and properties from Arthur Cayley, and then about 100 years later, you get another three scientists listed right here that rediscovered matrix concepts to discover quantum mechanics, which is called another field called matrix mechanics. And as for any definitions and properties, well, essentially it's any rectangular arrangement of numbers. So for example, A would be, it has two rows, as you can see, and three columns. It would be a 2 by 3 matrix. And for B right here, it has two rows and two columns. So it is a 2 by 2 matrix. And as for basic operations, addition and subtraction essentially work the same. I'll circle it out. Addition and subtraction works the same. As you can see, essentially you're just doing the same place element addition and subtraction. As for multiplication, it's also quite intuitive. You multiply these two, adding the multiplication of these two, you get an element here. Intuitively, you get something like this. And as for transpositions, it's just swapping the circled diagonal elements. Even if it's not a square matrix, transposition works the same. And to find the inverse, you do Gaussian elimination using this format, and then much later on you'll get something, an identity on the left and the inverse of whatever circled here on the right. As for common types of matrices, you have the identity that is all ones in the diagonal, diagonal matrices, which has elements only on the diagonal, zero matrix, which is all zeros, a symmetric matrix, where itself is equals to its transpose, a skew symmetric matrix, where itself is equals to the negative of its transpose, as you could see here with an example. An orthogonal matrix would be if itself multiplied by its transposition, you'll get the identity matrix, which is also saying its inverse is its transpose. And for permutations, it's essentially having at least a 1 in each row. So basically, it tries to reorder rows and columns of another matrix through multiplication. And as you could see, you have an example here. After multiplying a permutation matrix, you could see the elements are swapped. And as for applications, it could solve system of linear equations. It could do computer graphics, model real-world systems, do data analysis, and it's very helpful in quantum mechanics, as mentioned. It has a whole field called matrix mechanics. And as for the proper assignment, I'll open another file, as you can see here. So essentially what we're trying to do is to find the number of permutation matrices A such that A squared is equal to the identity and A is not the identity itself. So basically what this is trying to say is that if we're saying A squared is an I, where A is a permutation matrix, it is also saying it's a permutation sigma that belongs to the group, symmetric group Sn, whereas sigma squared is the identity and sigma is an involution in the symmetric group Sn, where an involution is a permutation that is its own inverse, and its cycle is only composed of fixed points and transpositions, so the cycle length is always less than 3. It has to be 1 or 2. Here, let the number of cycles be n, and the number of transpositions be k, and there will be 2k elements in k transpositions, and also you have n minus 2k fixed points, and because you would have you couldn't have a negative number of fixed points, you would know that k is belonging into this set. Well, more modified, it could look something like this. But it essentially works the same. And for fixed k, the number of ways to choose a transposition out of all involutions is n choose 2k. And the number of ways to perfectly pair 2k elements into k unordered pairs is essentially this number. And to find the number of involutions, because they're linearly independent, you could just multiply them together and you would have something like this. So that is essentially the total number of involutions. Let's call that IM for the time being. And then we're ignoring the identity element when we're counting the number of proper roots. So you would have the first equation that looks like this. This is the number of involutions for each k. So we need a summation that uses the condition that we mentioned earlier, and then sum them up all together, because you don't know, like it could be, the k could be 1 or 2 or 3 or 4 that is lower than this number essentially. And because it's very hard to code factorials in Python, we're going to use exponential generating functions to yield combinatorial recurrences, because recurrences are much easier to code on Python. So here is the exponential generating function of in. After a bunch of calculations, you would have this value. And differentiating that also gives you a recurrence back to this relation of its original. And then this is how you compute the differentiation of ix. This is how you'd compute 1 plus x multiplied by ix. And you'd have something like this. And because of that, you could derive the recurrence relation for all n is greater than or equal to 1. And because, again, we don't count the identity, you'd have PSQRD n is equal to this value, in minus 1, where you'd have this recurrence relation and these base cases. And as for the code, let's head back to what we had just now. Here is a function that explains how you get those 20 values. So these are the base cases. This is the recurrence. And you minus 1 at the end to get the real values. And then you print them. As for the matrix generating functions, this is the number of single transpositions. So you swap once. So you swap once, as you could see. You get the identity first. You get the diagonal elements to zeros, and then you swap the other ones. As for double transpositions, you only get 3 sets. So there's 3 ways to partition 4 numbers 0, 1, 2, 3, and then you swap them. That's what this part is doing. And then afterwards, you would have something like this that tries to print all of the generated matrices. And before we head out, let's explain more on what one of these examples is doing. So this is saying 0, 1, 2, 3 is the location of ones in the original identity matrix. As you could see here, that's the identity matrix. And 0, 1, 2, 3 swap is saying you have a matrix like this. And that concludes my video.